Okay, welcome to the ltspice tutorial. So I'm going to assume that you know absolutely nothing about ltspice, and we're going to start from the very beginning. So this is the opening ltspice screen, and you click New Schematic to go to the gray screen, and this is where you can put down components to make your circuit. So the very first thing we're going to do is we're going to model the signal generator that we've been using for this lab. So the signal generator of the M2000. So the signal generator consists of a voltage source and a resistance. So let's go ahead and make the voltage source. To do that, you can just press V, and you'll see your cursor changes to a voltage source symbol, and click to place it down. So now we're going to place a resistor, because we're going to model the internal resistance of the signal generator as a resistor. So to do that, press R, and you'll see your cursor becomes a resistor, and then you can press Control R to rotate it, and place that down as well. So now we want to connect these two. So you can either click the wire icon, you can click icons for any of these, but it's also nice to use hotkeys, or you can just press F3. F3 is the wire hotkey, and then connect the voltage source to the resistor. So now we want to add some grounds. So to add a ground, you press G, and you see your cursor becomes a ground symbol, and we'll place these down right here and connect wires to them. So right now we've just simulated the signal generator, but nothing has values yet. So the resistor, we're going to right click on it, and in the resistance field we're going to put 50 ohms, because we expect that our signal generator has an internal resistance of 50 ohms. So great. Now what does the voltage source do? Right now, nothing. So we need to right click it, and you could set a DC value, but we're gonna set a sine wave instead. So click Advanced, and in the function section, you click sine, and we're gonna give it an amplitude of 5 volts. So this isn't peak to peak, this is just the raw amplitude. So you'll see here that it actually has a parasitic properties tab. So we could have just given the signal generator series resistance of 50 ohms. But I think for the purposes of explaining this to you, it's better to have it as an external resistor. So we're going to do that instead. So now we have a sine wave. You should also set a frequency for it. So let's say 10 hertz. Now we can click OK. Now, if you click run the simulation, you can click the running person to run the simulation. It's going to ask you what you want to run exactly. So it'll take you to this edit simulation command tab. And for our very first simulation ever, we're going to run a transient simulation, which means it just simulates it for a given length of time. There are a lot of options here, but we're just going to use the stop time. So we're going to simulate it for 1 second. So we generated a signal of 10 hertz, so we expect 10 pulses in our simulation. So okay, click OK. And you'll see anytime you click the running guy, this black window pops up, and it'll show you the results of your simulation. So you'll probably notice that right now it's showing absolutely nothing. That's because I haven't probed anywhere in my circuit. So there's only one place in my circuit that I actually can probe, which is the area between the voltage source and the resistor. And we're going to go ahead and click on that. And there you see we have our sine wave that we set up on the black window. So obviously this isn't very interesting, so let's move on to something a little bit more complicated now that you have your very first simulation under your belt. Let's go ahead and build the oscilloscope. So in the lab, we said that the oscilloscope is a resistor and a capacitor in parallel. So let's go put that down. So press R for the resistor again, and C for a capacitor. Let's put them next to each other. All right, and let's connect these two, just like in the diagram in the lab. And let's also connect this to a ground. All right, and let's give these values that we should expect. So I'm going to go 186, is we should have a 1 mega ohm input impedance and input resistance, sorry. And let's go 30 minus 12, 30 picofarads. So 1 mega ohm and 30 picofarads. Now, let's form one of the voltage dividers that we would have used during the lab. So let's say you had a simple voltage divider circuit. So let's put down another 50 ohm resistor. And let's get this 50 ohms. Let's connect the two resistors, and let's connect this all to ground. All right, and let's pretend that we're going to make a measurement with our simulated oscilloscope. So we're going to connect our scope to in between these two resistors because we want to test the value of this voltage divider. So this should be pretty close to the actual experiment that we ran. So we're actually modeling the internal resistance of the scope and its internal capacitance. So let's see what this looks like. So run the simulation again, and let's measure what the scope should see. And yeah, see 2.5 volts as you would expect. You can set up different measurement points, so you can also measure before the first 50 ohm resistor. So if you want to see how things relate to each other. And another nice thing to know about is that you can also export this data if you want to look at it in another plotting program, because maybe you don't like the horrible ltspice plotting software. So you can go export to data as text. At some point in this lab, we were sending AC signals into the scope and seeing when they attenuate. So let's see if we can understand this a bit better by explicitly simulating it. So, by the way, if you want to delete sections of your circuit, just press the delete key and this pair of scissors will show up and then you just snip away. So let's put the scope in a different position. Let's pretend that we're just sending a signal straight into the scope. So let's move it to the other end of the resistor. So, all right, let's try to simulate an AC signal into the circuit. So instead of using a sine wave, we're going to go to the voltage source, right-click on it, and we're not going to use a function. It's quicker just to say we have a 5-volt amplitude AC signal. So put 5 volts into the AC amplitude field and click OK. Let's go to simulate and edit simulation command. So previously we've been running simulations for 1 second with transient analysis. So we're going to get rid of that and go to AC analysis instead. And let's go for an octave sweep. So we're going to sweep over frequencies and basically produce a bow plot as to how the circuit responds to frequency. So let's say 1 point per octave, and let's start at 1 hertz, and let's go up to, let's see, about 10 megahertz, I'd say, and click OK. And now we click run. So let's run the simulation. And let's see what our scope would see in this instance. And here you see the bow plot. So see the signal starts full and then it starts to decrease as you get into this 10 kilohertz range, which is basically what we saw in the Adel 2000, right? And that's what we calculated. So I'll leave it to you to figure out the rest, and I would recommend replacing all these figures with ones that you actually measured and let you draw your own conclusions from here.